Hello again. This is Math 2115 coming to you from the College DuPage, and this is the conclusion of the lecture entitled Pascal's Formula and the Binomial Theorem. Make sure that you are an active learner as you watch this video. Recall from last time Pascal's formula. N plus 1 choose R is the sum of n choose R minus 1 plus n choose R. We will use that a lot in this lecture. We can use Pascal's formula to derive new formulas from Pascal's formula. So this exercise says use Pascal's formula to derive a formula for n plus 2 choose R in terms of n choose R, n choose R minus 1, and n choose R minus 2. And of course, for this to make sense, we have to have R is between 2 and n inclusive. So let's begin. So by Pascal's formula, now we're applying it to n plus 2 and R. We get that n plus 2 choose R is the same as n plus 1 choose R minus 1 plus n plus 1 choose R. But if we apply Pascal's formula again to this one, we get that n plus 1 choose R minus 1 is n choose R minus 2 plus n choose R minus 1. And if we apply Pascal's formula to this one, we get that n plus 1 choose R is n choose R minus 1 plus n choose R. If we add these together, this term stands alone, this term stands alone, but these two terms are identical, and so when you add one of them and another one, you get two of them. And we have shown this expression in terms of those three. We'll now turn our attention to a very important theorem called the Binomial Theorem. And in algebra, a sum of two terms, such as a plus b, is called a binomial. There are two terms, just like a bicycle has two wheels. The binomial theorem gives an expression for the powers of a binomial, a plus b whole to the n, for each non-negative integer n, for all real numbers a and b. Now, it is instructive for you actually to do a few of these. And so if you take a plus b whole to the 0, you know you get 1. A plus b to the 1 is a plus b. A plus b whole squared is a squared plus 2ab plus b squared. You remember the middle term. If we cube it, we get a plus b whole cubed is 1a cubed plus 3 a squared b plus 3 ab squared plus b cubed. And so on. Here we go down to a plus b to the 5th. Now this doesn't prove anything yet, but notice that these coefficients that are shown in red here are the same as the coefficients in Pascal's triangle. So that gives you reason to believe that there might be a theorem like this, which is the binomial theorem. And that's given any real numbers a and b, and any non-negative integer n, a plus b whole to the n is the summation from n equals 0 to n of n choose k, a to the n minus k, b to the k. And if you write that in an expanded form, this is what you have. So you start out with 1, you go to n, and then you have all of these other binomial coefficients. And those are, like n choose n minus 1 here. So, and realize that since this is n choose 0, that is 1, and this is n choose n, that is also 1. Now, we do have to remind ourselves that a to the 0 is equal to 0, and a to the n minus 1, if n is greater than 0, is a times a to the n minus 1. And we'll use that in our proofs. Now we are going to look at two ways of proving this. One just using algebra, and this is kind of involved, but you should work to follow these steps. And the other way, we're going to talk about this, doing this with induction, and I think we'll even talk about a combinatorial argument. So here we go. And actually this is the induction proof, but it does involve algebra. So we want to show that a plus b to the n is equal to this sum. And so this is going to be the expression that we have for Pn. But we have to start where we want to start, and we want this to be true for all numbers, all positive integers rather, bigger than or equal to 0, and 0 is not a positive integer, so it's all integers bigger than or equal to 0. So we have to show that the first one is true. So when we put 0 in for our exponent, we see that this is equal to this, and if we do all of these calculations, we'll find that it is 1. That means P of 0 is true. By induction, then, remember that we have to, we're going to prove this. If P of m is true, then P of m plus 1 is true. That means this is our induction hypothesis. So we're saying a plus b whole to the m, and that is the summation from k equal 0 to m. M, choose k, a to the m minus k, b to the k. That is our induction hypothesis. We're assuming that's true. That's the if part. And we need to show this, that a plus b to the m plus 1 is the summation from k equals 0 to m plus 1. And this is m plus 1, choose k, a, and this is to the m plus 1 minus k, b to the k. So you see that is the conclusion that we have to show. So what we're going to do is we're going to start with this and show that it's true. So we know that a plus b to the m plus 1 is a plus b to the 1 times a plus b to the m. And we're going to apply our induction hypothesis to this part. So it's a plus b times, and then this is our induction hypothesis. This is what we're assuming is true. So you see, we can replace this with this. And now we're going to distribute this expression across a plus b. So it's going to be a times this business plus b times this business. And we'll distribute the a through. That makes this a to the m plus 1 minus k, b to k, and that makes this one b to the k plus 1. Okay, so this is an important step. And now we're going to transform the second summation on the right-hand side by making a change of variable. J is equal to k plus 1. So that means that m choose k is m choose j minus 1 times this, which is this. When we simplify, we're distributing the minus sign across, making that a to the m plus 1 minus j, b to the j. So the second summation on the right-hand side becomes this. But j in this summation is a dummy variable, so I can really start this one at 0 if I choose to. And but the j in the summation is a dummy variable, so it can be replaced by k. And so we do that. And then we can substitute back into our original equation, and you see what we have then is both are sums on k. The reason we did this is that we want these powers of a and the powers of b to match. Now we will have to strip out the first one by itself, but then we can start with k equal 1 for this one, and we have this expression being added together. So this is going to be a to the m plus 1 plus, and then I can simplify this expression by, since these are the same terms, I'm combining like terms. So I get this one, plus this one, plus this one, and we have already proven that this is the same as m plus k, and then this is m choose k minus 1. But this is the same as this by Pascal's formula. Think through all of this. This is important kind of calculations. So this is equal to this, which is equal to this when I sum from k equals 0 to n plus 1. And that's what we were supposed to prove. So you see, by mathematical induction, we have proven that this is true. The binomial theorem is true. And it is instructive to write out those products like I said. And in fact, we call n choose r because it's the coefficient in this expansion. We call this the binomial coefficient. Now, here's another proof using a combinatorial argument. And here, this is kind of a mathematical point, but if we're counting, we can't count with 0, but we've already proven this using induction starting at 0, so we're just not going to prove that part again. But now, we're going to let a and b be real numbers, and n an integer that is at least 1 or greater. N equals 0 was already proven here. So the expression a plus b to the n can be expanded into product of n letters, where each letter is either a or b. So it looks like this. So a to the n minus k will have n minus k factors of a, and then k factors of b. And this occurs as a term in the sum the same number of times that there are orderings of these. But we know how to count this because this number, how many times does this happen? This number happens, C choose K, because that's the number of ways to choose K positions in which to place the B's. And the other positions will be filled by A's. Hence, when those terms are combined, this is how many we have. And you see it is N choose K for that. So we will add them all up, and that was what was to be shown. This is a combinatorial argument. Sometimes I will ask students questions about substituting in the binomial theorem and writing out an expansion. And so here are two examples. A is just a plus b to the fifth. Well, a plus b to the fifth is going to be this sum from k equals 0 to 5 of 5 choose k, a to the 5 minus k, and this is b to the k. And you could use Pascal's triangle if you wanted to, but we have these binomial coefficients, which we can calculate, and we get this as the expansion. Here's one that's a little more complicated. We have x minus 4y to the fourth power. Now here it is important you realize the first term is x, but the second term is plus, and then it is minus 4y. So you see it's important to realize that that's minus 4y. So that means when we do this, we will expand it, and it's going to be the summation k equals 0 to 4 of 4 choose k, x to the 4 minus k, but then the second term is minus 4y to the k. Now when you start raising this negative to positive integers, it's going to alternate between being negative or positive, because a negative times a negative, an even number of times, is going to be a positive, and if it's an odd number of multiplies, it's going to be negative. So anyway, you write all that down, and you do the calculations, paying mind to the positive and the negatives, and you get this as an answer. It is very instructive for you to work through this and understand how these numbers come about. We can also derive another combinatorial identity from the binomial theorem. And so the question is, what is the summation from k equals 0 to n of n choose k? Well, you see, that's the same as saying, how many subsets of size 0 do you have from n elements? How many subsets of size 1, subsets of size 2, all the way to this? And so, when you go through that, this is the same as 1 plus 1 raised to the nth power, and that's going to be 2 raised to the nth power. So consequently, this identity is true. Let's use a combinatorial argument, and actually this is the same argument that I did. That was more of an algebraic argument, but the number of subsets of S is the number that are of size 0, of size 1, size n, and we know that that is n choose k each time. Those are disjoint, so we'll add them all together, and we get, again, 2 to the n. We can also use the binomial theorem to simplify a sum. So here we have the summation k equals 0 to n of n choose k times 9 to the k. Now, the key to doing this is to realize that this expression right here is a binomial expansion of 1 plus 9 to the nth power, because I'm going to have the summation k equals 0 to n of n choose k, and then I'm going to have 1 to these 1 minus 1 to the n minus k. That's always going to be 1 times 9 to the k. So you see this is always 1, so it's equal to this. But if I look at what this expansion is, this is really just 10 to the k. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself and of each other. May God bless you all.